Let's take a look at section 14. This is basically more on regression analysis, and we'll look at it a little bit further than before, but really not much further. I want to show you the Excel package that basically produces an ANOVA table, and then we'll be able to determine, without just kind of looking at it, how good the linear regression model is, and be able to reject or accept the model. So that's basically the point of it. So this is what we'll look at in 14, some general concepts again, some inferences, correlation will be the analysis part, and a little bit of interpretation. So we'll get through these types of sections. I'm not collecting homework, but the ones you should look at, I actually changed this to 12.6, 12.7. Those are just basically a little more straightforward. Don't need to do 12.9 unless you just want to try it. So I'm doing kind of a hybrid in between, just going over my notes versus writing everything out to save some time, especially when it's kind of more discussion and less actual math calculations. So here's the idea, and if we've done it kind of similar, that's okay. We're doing it again. Suppose I want to find out what, so we want to talk about an example, of what's this regression thing look like. Suppose I want to find out what study time worked best for learning mathematics, or how about this stat class? What might I do to find out? So I could ask a class or a number of classes, how much did you study? And then I can plot, how much time, and then I can plot their scores. I can plot their overall scores, their final exam score, kind of whatever I want. But that's the sort of thing you could do. So what formula might I create for a predictor of success? So this isn't like a really good example, but just it's very tangible of what you could do. So suppose we didn't know, like how much study time, and we're not necessarily assuming it's you study more, you do better, but let's assume that it's some sort of linear case. So we assume it's some sort of linear relationship. So let's suppose I asked a bunch of students, asked all of you, and this is what I came up with. Okay, so had that data all ready to go, and you should have the lecture notes anyway, but still you should write out rewrite just about everything when you're doing this. So the time is, you didn't study at all, and you got 20%, or doesn't really matter what it is, just you got 20, and this is out of maybe 100. So total is maybe 100 out of here. It doesn't really matter. And then maybe this is in hours. You study a total of 5 hours, 10, 15, 20, 25, 30, 35. I made this an even amount, or like a demarcation. It wouldn't necessarily be like that. I just kind of did that for ease of plotting. And then I plotted this, and I wanted to see if it was linear. Now, of course, I just made this up, so it is linear. But it's not exactly. It doesn't line right on, line up exactly on the lines. So we can plot all this. Let's suppose I plot this. Let's just use this color. That's fine. So I'm plotting this. 0, you're at 20, which is here. 5, you're at 40, which would be here. 10 would be 45, which would be here. What I missed? 15, 5, 10. Oh, this is a little off. 5, 10, 15. I needed to keep going. Oh, what happened is I changed this earlier, and it kind of messed up the way it was done. So we'll just extend this out, and I can just redo it. No big deal. What is it? I hate when it does that. Okay, so let's use the same color. I'm a little picky about that sometimes. So 5, 10, 15, 20, 25, 30, and 35. There's 35 was the maximum hours. Yes. This will match what I plotted on the computer better. Anyway, so 5 was 40, right? So 5 was 40. Let's bring those over. 10 was 45. 5, 10, 15 was 65. Should be here, so you can see those are a little off. So 15 was a 65. Could be 15 days. I don't know. It doesn't really matter. You get the idea. But this is what you do. You plot them. You see if it lines up in a linear fashion. 20 was 70. 25 is 85. 30 was 93. Just kind of guess. Just draw a big dot. It's good enough. 35 was 90, so that actually dipped down. So that's my line. It looks pretty linear, but now we'll be able to see how linear essentially. So now you have a line that goes through them, and you know that line, who knows what exactly it is. I think it basically looks a little higher like that. Okay. So we'll be able to graph that line, which we did last time, but this will give us basically a p-value. That's what we'll end up getting. Okay, so that's the idea. If you're not familiar with graphing lines, this is when you need to do it. Just look up graphing linear equations. And it needs to be at the algebra level or in your needs to be at the intermediate algebra level, because sometimes you get levels that are too high or even too low. All right, so what the idea is, we calculate this line. We calculate this line using what's called the least squares method. And I will show you some of the formulas, but we're not going to actually do them in this case. You may. Those will be a couple of homework questions. You can do it, but I'm going to try to show you and turn the camera and show you on Excel, because I can't. It turns out some of the features are not on my iPad system, or I can't find it, and I'll show you on there. I'm basically assuming most of us can find Excel. It's really everywhere. If not, just let me know, and you have the printouts anyway for the quizzes, so it's not going to be a big deal. So least squares method, and what am I saying? And it's called a regression line. And it's called a regression line. So when you hear regression line, it's the basically best fit line that goes through those points. And let me show you something here. Let's change this to the gray. This goes a little farther. I meant to have that go farther. Nah, it didn't work. We'll just extend it. What you calculate when you're doing this are these errors. So you look at this distance and this distance and whatever else you can find. These, I lined it up pretty well, so it's not a big difference here, but not a good example maybe. And that's what we'll look at. So in the book, there's some more theoretical aspects of it, and you look at this actual regression line, y equal to beta x plus alpha. And then they say plus epsilon, where epsilon is the error. Where epsilon is the error. So they get into that a bit. I do want you to read through it, try to grasp what's going on, and then we will proceed. So, method of least squares, or principle of least squares, we do these calculations. Let me make sure I have everything written. Okay, so we estimate the actual line, which is the y equal to beta x plus alpha. And I wrote this somewhere. Oh, they like to flip that around. I don't know. These statisticians, I guess, they write that as alpha plus beta x. Other books will use, like, I think something like this. They'll do like beta 1 plus beta not x. They don't use it in this book, but that's sometimes what they're referring to. These are the coefficients. When you see coefficients, that's what they're talking about. And we'll look at how good a fit those coefficients are to an actual line. Okay. All right, so we estimate that actual line with y hat equal to bx plus a, or those stat people will write a plus bx to just confuse us, I guess. So B is an estimator for beta, and of course A is an estimator for alpha, and A is an estimator for alpha. Okay, so we estimate alpha and beta by these formulas. So B is SXY over SXX, and A is Y bar, which is the mean or average of all the Y values, minus B, which you just calculated, times X bar, which X bar is the mean of the sample Y values, X values. Okay, so X bar, Y bar are the sample means. So you go back to these here and you average those, right? And you average those. And that's how you can calculate. It's actually not too bad of a calculation. You can do all this pretty straightforward. I didn't mean to leave those, but I left what they are. SXY is this calculation. I leave off the they make another formula that's called a calculation formula, the one you would use if you're doing a bunch of these calculations. We're not really doing that, but you can just use that one if it's, for this small data set. So not a big deal. So these are the individuals, that's the mean. These are the individual values, that's the mean. You do the subtraction, you multiply, and then you'll have a bunch of them, and you add them up. So that's your SXY. SXX is the square of that. So you square each individual term, and then you add it up. So I runs from, which I didn't write here in my other notes, but basically you're adding them up. I goes from 1 to n, or however many, whatever your values are. And for regression, they have to match. You can't have, fewer here and more here. They have to be the same because you have to have a pair. Okay. All right. So, so these formulas allow us to calculate the best fit line of the ordered pairs. Now, why this works and why it is the best fit, well, that's beyond the level of the course. That uses it's basically not until multivariable calculus. I do see those a lot when I'm teaching that class, but we don't end up doing it. Maybe I should. I end up skipping often that because it's more stat stuff and we need to move on to focus on other things. But it is in those sections. I've seen them many times in the Calc 3 stuff or multivariable. So you can prove those concepts in there. So if you have a small data set, you can just use these formulas to calculate the regression line to figure out those coefficients A and B. All right, so let's go on now. So the analysis of variance, this allows us to determine how good a fit it is. And just it's kind of like it's hypothesis testing. Is it good enough at a certain alpha level, and we can accept or reject it as a good fit? Are they correlated or not at a certain level? And we'll talk about correlation here in a second. So the total sum SS SYY is the sum of the y's, the dependent variables. Yi minus y bar squared, right? That's really the same as this one, but they're the y's. But to get y, you have to do this calculation. Those are your y's. That's your average. Actually, you don't need that calculation. I'm sorry. You don't need that calculation. You just need the y's. SSE is the sum of y sub I minus y hat I squared. And SSR, this is what we would have seen back into the ANOVA stuff. Y sub I hat minus y sub I bar squared. And we can show, that SS is equal to SSR plus SSE. That can be done algebraically using those other, not directly, but using those other calculation formulas and work that out. We don't need to. So if you're going to do anything, these leave it to computer packages. If you want to try one, it's good to do this one and just calculate that by hand. But you won't have to do that either. So let's check one out. So we can calculate an ANOVA table. We will let Excel calculate it. So let's look at the time and performance on exam question. Find the regression line and output an ANOVA table. Okay, so that's our question. That's our example. Then test the usefulness of the model. So that's going to be the ANOVA table, and I'll show you where you get the p-value. All right. By interpreting an ANOVA table at alpha equals, what did I say, 5%, right? So 0.05, that's pretty typical, right? 0.05 is your significance level. You always want to ask at what significance are you testing at? And it'll be a lot different on what you're looking at. When you look at medical stuff, The significance level is well, it's really, it has to be a high significance, meaning your alpha is very small. You don't want, it depends on what what you're looking for and what might happen. Okay, the test statistic we use looks like this. And I didn't write that one out, but we won't have to actually do this. This is what is calculated by the computer package. The test statistic T is B minus beta naught over the square root of MSE over SXX. And again, that we'll let someone else do. And the degrees of freedom is n minus 2. Basically, because you end up having two samples. It's the x and the y, and so you subtract by 2. Won't get into the theory. And we use the student t-test. So this is the student t that's being used for that test statistic if we're going to accept or reject the null, which the null is that they're not correlated. The alternate would be they are correlated. Okay, so HA, H naught, sorry, the null is beta equals beta naught. And then usually you say beta naught is 0. So it's not a line, essentially. It's like horizontal, there's no correlation. So versus, and then you have the other cases, right? So for HA, we have beta is greater than beta naught, or 0 or less than. So it's either a positive slope or negative slope is less than beta naught, which is usually 0. We're pretty much, you're going to assume it's either 0 or not and see what your alpha level is. And then so those are the tails, and then 2 tails is beta is not equal to 0 or not equal to beta naught. Basically beta not equal to 0. Okay, so let's go ahead and do this calculation. I have the output below. Going to try and show you the screen here. Let's see if this works. I don't think that's working. All right, so maybe that'll work. If not, I'll just talk you through it. All right, so let's pretend this isn't plotted. And so we're going to copy that, and I'm going to put it in another table over here. Okay, so now let's copy that, and this I have to figure out how to do it every time. We're going to insert, and we're going to look over here for the graphs, and we're going to do scatter, and you're going to pick the scatter plot like that. That doesn't look like what I had earlier, huh? And then you're going to say, well, add chart elements, and we're going to do trend lines, linear. And I missed something. You're going to add trend lines. There's something else. Oh, yeah, then you got to click on quick layout. God, this is always a pain. And then see the function? That gives us the function. And there it is. Not sure you can even see that on here. Hopefully you can, and zoom in. This is trying to look at this right there. And again, I can't get this to get bigger. I've been trying. It's computer stuff. So your y is 2.0952, intercept 26.8. So see how it's higher up here? And there's your correlation. And it gives you r squared. So to find r, the actual correlation, you just take the square root. Okay, so that's how you do that. And while I'm here, let's see what it's doing. Let's back up a little bit so you can see. That's going to have to do how you do the next thing. So now we're going to do the output. So that we're going to do regression output. So you copy that, and then you have to go to data, and then you go to analysis tools, and you click on analysis tool pack and hit OK, which I already did. And then this will pop up, data analysis. And you have all these different data analysis things to do, ANOVA, single factor, etc. I have it on regression, and I hit OK. It tells you everything that you want to do. Labels, that means does it have headers at the top? And I do. I'm gonna, because I highlighted it. See, I highlighted that. Confidence level 95%. That's your alpha. Regression output example. I'm going to change that to regression output example 2, because I already have another one. I have the original one on there. And then you got to look at your Y range. Y range looks good. Otherwise, you just click on it and highlight. X range looks good. Or I use T, but it's still your X. It's your deep independent variable. Okay, so that's all fine. Okay, and then this gives you all a bunch of other stuff. You don't really need any of it. I did the line fit and the residual plots. We can talk about normality and all that. Then you hit OK. And then it gives you an output in a whole nother sheet is what that meant. So here's your output. I'm going to show you this output on the computer now. So we're going to go back. Okay, I am back. So let's go to this. Oh, so there's my output. I calculated R, so that's pretty close to 1. The closer it is to 1, the more it's a linear relationship. But again, we're not going to guess anymore because we're going to go to the table. So here's the output for the Excel table. It gives you a ton of stuff. We only need to know a few things. I want to point out a few things. So one of them is, here's your coefficients. If you go back up, coefficients are 26.833, and there you go, 26.833. So that's your intercept, and that's what it says. And then here's T. That's because I labeled it T. And then, so that's your beta. Okay, so that's your coefficient of X, or T in that case. Okay, then you have standard error. So here's your t-test statistic. Those are very large, but it actually gives you the output. So here's your p-values. And you can see that those p-values are quite small. And we knew it had to be close to linear. I mean, I made it up and it looked perfect. So p-value is less than alpha, which equals 0.05. So we say the relationship is highly likely it's highly likely that correlation exists. So I would say therefore it is highly likely that a correlation exists. And that it isn't, the other thing they might say, it does not occur by chance. Okay, so one thing I want to strongly state is do not claim causation. Now, that is more the scientific method and repeated ways of showing that doing this causes the other thing. The issue many researchers get into and is a problem is you can show correlation by doing this type of stuff, but why one occurs and not the other is a whole different thing. Causation is very difficult to prove, and I see it all the time in education research, medical. You have to maybe more, they do that a little more carefully, and you have to have a very well set up experiment. And that's where the next classes will come in for experimental design. Is experimental design helps you flush out whether there's causation versus just correlation. Okay. So maybe I'll bring that up in the next example. All right. I think that covers most everything for regression that we will be doing. And next we move on to categorical data.